Have you ever wondered, how does a laser work? Or has the thought of building a laser yourself ever crossed your mind? Probably has. I mean, who as a kid did not shoot people with lasers? At that age, we were sure that lasers came from outer space, from a far, far away galaxy where Jedis and... Oh, never mind. Wrong script. Did you know that lasers was an acronym? For some who don't know what acronym is where each letter of the word represents a word. Laser stands for light amplification by stimulated emission of radiation. Wait, whoa. Stop, right there. What does that even mean? Let's take a few steps back and go to chemistry class to learn about the atom first. Imagine we have 3 bowls. In one of them, there's liquid, the other gas, and the other solid. First one, there's table salt. The other one, there's water. And the last one, there's oxygen. And that we can zoom in using an extremely powerful electronic microscope, capable of observing a little atom in each bowl. So we could probably get something at this. Okay, let's look at what an atom looks like, because I myself am quite curious. In every atom, there's a nucleus, which consists of protons and neutrons. Note that protons are positive and neutrons are neutral. Then on the outer rim, we have the electrons. The electrons aren't moving. This is just diagram. Nonetheless, electrons are negatively charged, and we all know that positive likes negative, and we want to be together. That is why the electron stays with the protons. They like each other. Neutrons are there to keep the structure of the atom like the foundation of a building. Here is a diagram of an atom, with its electrons around its protons and neutrons. These electrons are an orbital. The exact definition of an orbital is a space where there is a 90% chance of finding an electron. So, to put it into perspective, let's draw another diagram. An orbital can be found on these circles around the proton, like here, and there. These rings are different energy levels. The closer it is to a proton, the lower energy it has. The first energy level can contain up to 2 electrons, and the rest of the energy levels can contain up to 8 electrons. When we want to describe the shape and structure of an electron, an orbital, we refer to quantum numbers. Quantum numbers are what describes the size, the shape, and orientation of the orbitals. Like before, we saw orbitals can be in different energy levels. This is called the principal quantum number. It uses the symbol n. Like in this first ring, it's n equal 1. In the second, it's n equal 2. In the third, it's n equal 3, and on and on and on. As the quantum number n increases, the energy that these orbitals have increases as well. Remember that this is where an electron could be. It might not be there. I mean, an orbital is a 90% chance. 90%. 10% could be there or not. Next comes the secondary quantum number. It's inside the energy level, or the principal quantum number. There is a sub-energy levels, and the secondary number describes the shape of the sublevel. This number is given the symbol L. Subshells have different shape and powers. There is S, P, D, and F. Each have different shapes, like S has a spherical shape, P is in dumbbell, D is in a cross. Oh, and I'm sorry, I drew that wrong. And finally, F orbital is too complicated to draw. Now, imagine we cut the atom like a pie. We take a piece of the pie and we get a triangle with each different energy levels. The first energy level, the tip of the pie, only has a S subshell. Then the second energy level has a S and a P subshell. Then the third energy level has a S, P, D, and lastly the fourth has a S, P, D, and F. This is easy. The number of and an energy level is equal to the principal quantum number, n. Now, what do these sub-levels do? S contains 1 orbital, P contains 3 orbital, D contains 5 orbital, and F contains 7 orbital. So, sorry if you can't see perfectly, the light is reflecting. Now, remember that each orbital can fit 2 electrons. This is really, it can get a little confusing. That is why, let's get some hotel rooms for the orbitals. The first floor only has 1 room, and only 2 electrons fit, which makes it an S level. Let's assume every electrons are coupled, so they can share a bed. The second floor has 2 rooms, one with 1 bed and the other with 3 beds. 2 electrons go to the S room and 6 electrons go to the P room. Then on the third floor, there is 3 rooms, a S room, a P room, and a D room. The D room has 5 beds. Now, let's recap. A S subshell can hold up to 2 electrons, a P subshell can hold up to 6 electrons, and a D subshell can hold up to 10 electrons. These patterns can also be seen in the periodic table. The sublevel that has the most energy creates different group. The S group on the left, where the alkali and alkaline are, the P group to the right, and the D group in the middle with the transition metals. And finally, the F group at the bottom. These sublevels are written this way: the letter in front, which means the sublevel, and the arrow representing each an atom. The line beneath represents an orbital. Now, with this knowledge, we can start to understand a bit about lasers. Just how does light come out? The process all have to do on electrons. In special glasses, crystals, or gases, when an electrical current is passed through the atom, the electrons get all excited and move to the upper energy level. Now think about before, which quantum level has changed? Yes, it is the primary quantum level with the symbol N. Now that the electrons are in the upper energy level, they want to go back to their ground state, and in order to do that, it has to release energy in the form of photon, which is light with a certain wavelength. That is a lot of information, so let's recap once more. The electrons with the electrical current get excited and are able to pass to the higher energy level. However, they eventually want to go back to their previous state and have to release some sort of energy. In this case, it is light. Here, in the following diagram, we can see that the electrons in the second energy level moves to the third energy level because of the current, then has to go back to the second energy level, but to do so, it has to release photon energy. Imagine a tube with plenty of atoms in it. We have a lot of atoms releasing a lot of photons in all directions. This is called spontaneous emission. This is a bit like a glow-in-the-dark object. But in lasers, it is different. We need stimulated emission to occur. As the photons are released, other excited atoms are releasing photons, and so the wavelength gets bigger and bigger and intensifies, bouncing back against the mirrors. It gains the ability to gather a lot of energy. So, in a laser, there is a mirrored end and a partially mirrored end. While the photons bounces back and forth between the mirrors, a small portion of wavelength gets passed through the partial mirrors to release the light. The atom in which the current passes determines the wavelength of the photon, which determines the color of the laser. This is all there is to know on how a laser works. Not too hard, is it? Did you know that the fact of treating illnesses with light has been known for over thousands of years? The ancient Greeks used sunlight therapy, which they believed helped a lot thanks to their god Apollo, who takes responsibility for light, and healing. Now, I'm sorry for my drawing. I'm doing my best. Lasers has only been invented 50 years ago, and the year afterwards, medical laser was developed by Leon Goldman. He created a laser which could emit red light and could remove port wind stains in the type of burn mark from the skin. Lasers are definitely better than sun therapy, don't you think? Lasers rely on the emission of a very narrow and specific wavelength. That way it can focus on a very small point, giving them high power density. That is why lasers are now used for things like tattoo, hair, or birthmark removal. In this wavelength chart, we can see that each color has different wavelength. For example, red has a longer wavelength than blue or green. Lasers emits different kinds of colors depending on the wavelength. Difference between a toy laser and a medical laser is that the wavelength and the intensity are not the same. Medical lasers focus on areas with great precision, while toy lasers only emit light with a weak current. You can't really practice dermatology or ophthalmology now without access to lasers. They are mainstay tools in what we do for patients. This is said by R. Ox Anderson, a dermatologist at Wellman Center for Photomedicine, Harvard University. This highlights deeply the necessity of lasers in modern days. The type of lasers depend on the type of lesion being treated and what the main absorber is within it. It also depends greatly on the patient's type skin. The lasers that is quite interesting is the eye surgery laser. Ophthalmologists use argon lasers. Argon is a type of atom, and to be precise, it's a noble gas, which emits green wavelength light to treat detached retina in their eyes. The laser contains a single wavelength and has great intensity and narrow beam. The highly focused powers from the lasers amuses the retina to reattach. The green color and its short wavelength is ideal because it passes through the eye lens without being strongly absorbed, so it does not take a lot of damage. The lasers uses that wavelength to create scars around the detached retina to reattach the retina. The narrowness of the beam helps a lot to focus only on tiny spots. Another reason why green light is used is because it is selectively absorbed by hemoglobin, which is found in the red blood cells. That plays a big part in order to seal off bleeding blood vessels in the eye. To recap on the eye surgery laser, firstly, it is extremely narrow. Secondly, it has great intensity. And then it is green because it is not absorbed strongly by the eye lens. Thanks for watching my video, and I hope you all learned new kind of stuff, and see you next time.